All right, so welcome to the deep learning class, everyone. We're gonna go ahead and get right into it since everyone is here. So the way we'll kind of be doing things is we'll be using Discord in case like you have a error in the code and you need me to look at it, so you can put screenshots of the code there. Can you guys see my deep learning slide screen first of all?
Yeah.
Okay, great.
Well, it's kind of
And
zoomed in to the top
what?
right corner. It's zoomed into the top left corner, but yeah.
Really? Maybe it'll fix when I go into present mode. That's strange, but yeah, I guess,
It's fine for me.
okay, it might just be like a weird full screen issue on Noah's end. But yeah, what I was saying is that this course will be more focused on concepts behind deep learning and AI. Since I feel comfortable, all you guys took research, so I feel comfortable that you'll be able to read the code. It's more like applying it to a much higher level concept, which is the fun part. Once you know how to code, then you can really explore new topics. And then code is simply a means of expressing what you want the computer to do. And yeah, so we will hop right into it. The way that it's going to work is we'll use, as I said before, we'll use the Discord for posting screenshots, since you can't do that in the Zoom chat. You can also type questions there, or you can feel free to just unmute and ask questions, since we're a small select group of students this week. And also, like we can use, I guess we can use the reactions, but what would be even faster is I have everyone's screen popped up. If you don't mind turning on your camera and just throwing up a thumbs up whenever you're ready. If not, that's fine too. You can just drop a thumbs up in the chat. But that way we can just, once everyone gets it, then we can just simply move on. But yeah, in this course, we'll be exploring a lot of higher level stuff. None of this will ever be covered in high school in any of your computer science classes. So you already have a big head start here for just being eager learners to get ahead. So great job on that. I really am looking forward to teaching this class, and I hope you guys are equally as excited to do so. And similarly, this stuff will be almost introductory college level. Sometimes it's not even taught as a freshman in college. We won't get into the nitty gritty like calculus and math behind it, simply because you guys haven't taken that class yet. And as a result, I encourage you to ask lots of questions, because you won't really truly understand it unless you ask questions. And the question doesn't have to be like you don't have to like actively think of great questions to ask. You can simply just say something like, could you please explain that again? Or I didn't get this part of it. And I would be more than happy to do so. So that since we just have you 5 students, we will take it at your pace. So until everyone understands every concept on every slide, I'm not going to move on. And as a result, we can really, really develop fundamentals in deep learning, which a lot of people simply watch a couple videos and they skip over the what it actually means and how it actually works. And as a result, I want to solve that issue by really walking you through every step of the way. All right, so I'll go ahead and hop right into the presentation. All right, and again, this lesson is going to be pretty slide heavy, or at least the first half or so. But I mean, if you want to, by the way, you can take notes. A lot of this material is taken from, like, I took my own handwritten notes a long time ago, and I was able to use that to develop a lot of these slides, and it really just helps it stick. And if you guys are interested in using deep learning for science fair and stuff, I made one deep learning journal, and then every time I did a deep learning project, all I simply had to do was copy a lot of the material down. So yeah, feel free to take notes if you want to remember it. And also you'll have the recordings, available to you. All right, let's get started. So there's a lot of this idea of these buzzwords going on, right? We have AI, we have ML or machine learning, and then we have DL or deep learning. So I'll probably be referring to ML as, or machine learning as ML and deep learning as DL, just for convention's sake and for short form for it. but we can kind of look at it as an all-encompassing bubble. AI is really what encompasses machine learning and deep learning, which are both subsets of AI. AI is the generic term. As it says, it just enables machines to mimic human behavior, right? A machine is now making a decision, looking at some sort of situation, extracting some sort of knowledge from a set of data, which is something that a human is capable of doing, right? And it doesn't just have to be very data-centric or CS-centric, right? Any machine that can mimic a part of human behavior is known to be an AI, right? We can kind of dive one step deeper into what is machine learning, right? So machine learning is a subset of AI, and this is more oriented towards statistics. So machine learning is extrapolating. We'll get into the formal definition of all of these, but basically using statistics to learn in this sense, right? If we think back at our regression and clustering models from the Python for Research class, right? The machine was able to learn some sort of trend. It was able to find the clusters or find the linear trend from the data. And as a result, it was able to fit to new data. Remember, we created those predictions and then we plotted them. And we could even draw that line further and further beyond even to what was available in our data set. And as a result, the regression model or the clustering model is intelligent of sorts. So we can also take even one more step down this ladder, and over here we have deep learning. Now, deep learning is what we'll be focusing on, well, simply because we have explored a little bit of machine learning in our last course. So super cool how each one builds upon each other. Now, deep learning is fairly niche. However, deep learning is extremely powerful. Some say that it's the most powerful out of all of these. However, deep learning isn't the solution for every situation. A lot of times people use deep learning for something that could simply be solved by machine learning, or more specifically by regression or clustering. That's like using a sledgehammer for a task that can be simply solved by a hammer. That's a very common analogy that people use when deep learning is simply not necessary for certain tasks. However, for very complicated systems, when we're performing very, very complex computations, sometimes computations where humans themselves don't know what sort of algorithm to construct, we can use deep learning, and we'll really understand what it means to train a deep learning model, or how a deep learning model gathers insights from a set of data, which could be like, it could have an idea as to what it is, or it just could have absolutely no idea what it is. So yeah. All right, so let's first look at machine learning specifically. So as I said before, machine learning is simply a method for data analysis. It uses algorithms to iteratively learn from data. So who remembers what the word iteratively means? Go ahead, and you can unmute or just drop it in the deep learning discussion chat.
Like to iterate through like data and like analyze each specific item in a set.
Yeah, exactly. And what sort of, I guess, what process inside of code uses iterations?
For loops.
Yeah.
Loop again.
Or really, yeah, any loops that we're looking at, right? And yeah, that's a great answer. Yeah, Shri got it in the chat as well. But yeah, that's what iteratively means, right? So we're iteratively learning from the data in our case, and we will use some sort of algorithm in order to do so. So yeah. All right, and then last but not least, it allows computers to find hidden insights without being told where to look. Did we tell the regression model where to draw the line? No. Did we tell the clustering model which points go inside of which cluster? No, right? It extrapolated these hidden insights simply from the data itself without being told where to look, right? So this is a very, very important concept again. And luckily, I guess since we don't have to tell it where to look, we simply, our I guess, responsibility as the data scientist or machine learning researcher is to design the algorithm in order to best locate these hidden insights without explicitly telling it where to look, right? We just have to give the computer all the tools that we could possibly need in order to make it the most accurate. But in the end, the machine learning model is making a lot of the decision. All right. So I guess before we move on, I'll pause for a second if there's any questions about what machine learning really means, or if this makes kind of sense. This should make a little bit more sense because we have worked a little bit with it, even though we never explored the formal definition. But hopefully that connection is being made. All right. Let's move on. If you still have questions at any point, feel free to interrupt me or just ask in the chat, and I'm monitoring all of it. All right. So let's hop into what a neural network is, right? So a neural network is, we can really think of it like a neuron, and we're going to go into the biological definition of a neuron later and connect it to how mathematicians have modeled a biological neuron to be very similar to, not extremely similar, but you can extrapolate kind of like a general similarity between a biological neuron and a mathematical neuron. As a result, these networks, or these neural networks more specifically, can solve tasks that other algorithms cannot, such as image classification, which is something we're going to explore in lesson 3 and lesson 4 on Wednesday and Thursday. And these, in today's lesson and tomorrow's lesson, we're going to work with regression and classification using deep neural networks. So we already created a linear regression model, but now we're going to use a deep learning model in order to create a regression model today. And it allows computer to find hidden insights without being explicitly told where to look. Again, this is exactly the same bullet point that was in the previous slide, right? So the deep learning model is also able to find these trends, these hidden trends, and the deep learning model more specifically so. A deep learning model is often able to find more complex trends that machine learning might not be capable of finding, because it might not be simple. It might not be simply a linear model or even a polynomial model of that sort. It might just be something that looks very, very strange, especially with image classification, right? How do we plot image classification on a line? How do we create a model to detect brand new images that the model has never seen before? Well, the answer is deep learning or neural networks. Those are interchangeable. So, yeah.
Sorry, is it, so neural networks, are they like a subgroup or subset of deep learning, or is it like just an entirely different group? Or
yeah, you can kind of imagine it like a bullet point inside of deep learning. It's not really like a subset, I would say. Deep learning largely involves creating neural networks, more or less. I can't think of a great other example that doesn't involve artificial neural networks, convolutional neural networks. What else? Recurrent neural networks, all sorts of things. I guess deep learning could also involve like natural language processing and a lot of complex computer vision. But oftentimes those revolve around creating neural networks as well. So you can think of them as a very related sort of thing. But here we have like a definition of what deep learning is. It simply refers to a neural network with more than one hidden layer. So if you're not taking notes, this would be something that I would say still go ahead and write down, or just kind of put it on a little notes piece, because we're going to come back to really what this means in a second. So it simply refers to a neural network with more than one hidden layer. However, we don't know what a hidden layer, or even what a neural network layer is right now, right? But we will get back to this in a second. But this is really the essence of what deep learning is, and I really want you guys to keep this in the back of your mind as we move forward in the slides. We will come back to this. All right, so let's talk about supervised and unsupervised learning. So what does having, I guess just the English term for it, what does having supervision mean?
To be monitored.
Yeah, to be monitored, to be watched over, right? Yeah, Shri, but watched over in the chat. Just like a teacher supervises the class or something of that sort. Now we can kind of liken this to what supervised learning really means. It means that we're going to train our model using labeled examples. So the desired output is already known. Let's take a look at two examples to really define what this means, right? So a labeled example, let's say we're looking at a data set that contains a bunch of emails. And on those emails, we already know whether it is a spam email and whether it is a regular email. So these labeled examples, by the way, are labeled by a human or by some sort of professional that's able to classify these examples. So we have a data set with not only a bunch of emails, but the data set also tells us whether the email is spam or regular already. So we already know the answer. We already know the desired output. However, what we do is we feed in the unlabeled data into the model. We feed in all of these emails, regardless if they're spam or regular. We feed in all of this data into the model, and we tell the model that, hey, I want you to go ahead and classify these as spam versus regular. Now the model goes ahead and classifies which one it thinks are spam and which one it thinks are regular. And then from those, it's able to compare it with the labels that we already own, right? We already know whether the email is spam versus regular. So the model is simply checking itself versus what's known as the ground truth. The ground truth is basically like the answer key to the test. You can simply think of this as taking a test in class, right? You can think of the student as the model, and the student is simply marking down answers that it feels are the best in the test, right? We let's say we have A through D, and we're marking A, B, C, C, D, B, A, right? And we just mark our answers on the test, and the teacher has the ground truth. It has the known desired output, right? They already have an answer key to the test, and simply it is just comparing those answers that we put to the teacher's answer key, right? The teacher already has a desired output again, and we are simply training our predictions or our best guesses with the correct answers in that case. So this is where what it means as supervised learning, where we're trained using labeled examples, right? The answers to the test were already known. The emails, whether they were spam or regular, were already known. However, we're using that to train the model in order to compare itself to the actual classifications. And as a result, when the model learns from this data that we own, we can use this model to look at data that's never been seen before. So even though we've trained it on a data set of spam versus regular email, once it's accurate enough, you can give it an email that was not in the data set, an email that it's never seen before, and it's able to detect whether or not it is spam or just regular based on that, if that makes sense. We can similarly look at it as positive versus negative restaurant reviews. We can look at that as like sentiment analysis, where you're just using some machine learning to say, oh, this restaurant was 5 stars, or it was delicious, or so on and so forth. And some human has already gone through and classified these as whether they're positive or negative. And we're simply comparing what our model thinks it is with what the human grader, I guess, already pre kind of graded is. So does, I guess, I'll drop a reactions since only Noah and Shreyas have cameras on. I'll just drop a poll in the Discord. Does supervised learning make sense? All right, we got 3 thumbs up. And we got a thumbs up from Noah as well. And yeah, I think that is everyone. Okay, cool. All right. Let's move on to unsupervised learning. So let's say we won't be exploring unsupervised learning in this class, simply because we'll be focusing on neural networks with data sets that have pre-labeled data. Unsupervised learning is fairly niche, and I actually have yet to do a big project with unsupervised learning. However, it is still very fascinating. So what if we don't have labeled examples, right? What if we take our data set and we don't know any of the I guess true predictions, right? So this is very, very strange, and it's a new case, right? Oftentimes the data is not labeled for us, right? Imagine having I guess 100,000 images of chest x-rays, right? This is a common machine learning data set that's available online, or a deep learning data set. And those have already been annotated by a doctor. But how many types of medical conditions are going to have 100,000 images where a doctor has sat through and annotated all of them as to what condition they have, right? Very, very, very little of the data in our world exists as labeled data. So hence, supervised learning actually only solves for a little bit of what we have in the real world. And that's because, well, having supervised learning or having labeled examples requires human computation or human annotation. And that's simply something that's not easy to get by, right? Making a human do all of this manual labor simply to train a neural network, it's just something that doesn't exist nearly as popularly as just data that well, data is created from everything in today's day and age. However, labeled data is not created from every single thing that we have.
So supervised learning, after training it with labeled examples, can it eventually analyze unlabeled examples and
Yeah.
so
Yeah, that's exactly the point of supervised learning, actually, is to train it using some things that it knows that are true, right? You can kind of think of it like, I guess, let's say we're preparing for the you guys will have to take the biology star next year, or there are no star tests, but imagine you were going to take the biology star next year. Now, in pre-AP biology, you will be taking a bunch of tests pertaining to every topic of the biology exam, right? You're going to get your test grades back, you're going to learn from some of your mistakes, and so on and so forth. And as a result, you'll be able to, or you'll be ready to take the biology star exam, even though those questions are something you've never seen before, right? So as a result, you're looking at completely unlabeled data, or a test that you've never seen any of the questions, any of those wordings before, but you've been trained just like a neural network in order to, I guess, the concepts behind it, and more importantly, how to take the test or how to approach the questions, which is just unlabeled data in your case. And yeah, that's a good question. That is exactly how the process for deep learning works, is you train it using labeled data, and then you're able to extrapolate it, or you're able to fit it to non-labeled data, or data that the model has never seen before. So heading one step forward into unsupervised learning, where we don't have any data, can anyone remember an example? This should be singular. The one example that we looked at with where we looked at unlabeled data, where we did not have the labels for the data. Anyone remember? I'll give you guys a second to think of that.
Was that with the pictures on the last day?
Not with the pictures on the last day. We never really, I guess, extrapolated any results from the pictures on the last day. We did some image pre-processing and feature extraction, which we'll talk about once we start convolutional neural networks. But what was a data set that we had where we didn't know anything about it, yet we made some sort of, I guess, claims as to what the data set was showing without having any of the labels beforehand?
was it the Australian wildfire one where we had to edit a bunch of the labels and create our own columns?
That's a good thought, but we still knew. I guess when we were creating our new columns, I don't remember which columns we created exactly, but with the Australian weather data set, we were trying to find the hottest day of the year or the most rainfall rate. But that is a fact. That is a fact that's stated somewhere within the data set. We simply found it. So not quite unsupervised learning. There was never any learning that happened. We never created any sort of model that learned from our data. Think more along the lines of the machine learning lectures in the latter half of our program. Noah and Shreyas have taken a stab at it. Arush, Yamal, or Shri, any thoughts? And feel free to just take a guess. There's
Wait, was it possibly clustering?
Yeah, it was clustering. Nice. And the reason that it was clustering is because we had more specifically, it was the mall customers clustering that we looked at. If you remember how we had the 5 types of customers, we had the careless customers who had low income yet they had high spending. We had the medium customers that had medium income and medium spending. And we had 5 different types of customers, right? We had the cautious customers that were low income and low spending, and so on and so forth. So in the data set itself, in the data set of the mallcustomers.csv that we looked at, we never knew whether the customer was cautious or whether they were careful, or whether they were the target customer, right? We never knew that. The model never knew that. The k-means clustering model never knew that. However, regardless of that, it put it into 5 clusters, and those 5 clusters were very distinct. And based on those spending habits, we were able to come up with our own data for it. And yeah, that's a great example. And that is an example of unsupervised learning. In addition to clustering, such as k-means clustering, we can look at anomaly detection. That's basically looking for outliers. If you remember the box plots, an outlier is basically one of those dots outside of the whiskers, right? Outside of our 1.5 times IQR, if you ever did the math on those or explored what a box plot was doing. But the anomaly detection in unsupervised learning is obviously a lot more complex than just a box plot. And there's also dimensionality reduction. If you are ever interested in dimensionality reduction, we're not going to cover it in these 4 days. There's a lot of different ways in order to perform dimensionality reduction. It's very, very cool, actually. If you remember when we were doing the Plotly lesson, and we looked at the drugs on that 3D scatter plot, and then we took that 3D scatter plot and we put it into a 2D scatter plot. That is an example of dimensionality reduction, where you're taking a higher dimension and putting it into a lower dimension. Oftentimes, the dimensions are far more than just 3D, right? It could be n-dimensional, which is anything beyond, or any dimension, right? N is just a variable, and we reduce that down into 3D or 2D using something kind of sort of similar to clustering in a lower dimension. So that's an example of unsupervised learning. Again, that is much more complex and requires a lot more mathematical background, and we'll be focusing on neural networks in our class, but still very, very, very cool, especially unsupervised learning, thinking about what it's doing. It's learning from nothing almost. It's just learning from trends in the data and looking at similarities between data, but it's learning from no labels at all. And that's kind of mind-boggling to think about, right? Unsupervised learning is what spurs the fear of AI taking over the world or surpassing human intelligence, or all those kind of stereotypical fears that people have, where a machine learning starts to do what it's not told. And at this point in time, it's a little bit ridiculous, but unsupervised learning is the closest thing to it, even though it's far from being that capable. All right, so yes, for our class, we will focus on supervised learning. So let's look at the machine learning pipeline. Now, I'm going to spend a lot of time on this slide simply because you have to understand how a machine learning model works in order to create one, whether it's in code or whether it's on paper or in theory or so on and so forth. You have to know what the steps are. And now I know Shreyas was asking me, like, do we manually train the model, or how exactly does this work, right? So that's a great question, because, well, simply it's quite confusing until you actually explore what the pipeline is. What does it mean to train a neural network, or just any machine learning model in our case? And we can actually draw a similarity to our regression model, because we did a fairly similar thing. So we start out with preparing the data, right? We have some sort of data set. We want to remove the redundant data. We want to fill in all of the null data, right? This is things that we know how to do already. We want to format the data in something that is more readable. Let's say we were creating a neural network to predict on Fahrenheit temperatures, I guess. Remember, in the Australian weather data set, we had to convert it from Celsius to Fahrenheit, right? That's another part of preparing the data. And we'll talk about how to prepare image data and things that are more closely aligned to deep learning. Then what's next is that we have to train the model given our data that we've prepared already. So I won't dive into what training the model means in this slide, but this is what our supervised learning process really means. And yeah, you can think of training the model in our lesson. It's going to be our supervised learning process. Then what we can do is package the model. This is a step that we don't need to do for our lesson specifically. But let's say you wanted to take the model and you wanted to put it into an app, or you wanted to put it into a website. So you would first package the model, validate it, and then you would deploy it. And deploying means is to put it into an app or put it into a web server or so on and so forth. But with our packaged model, we can validate it. Now, validating means using, we're going to talk about a test set and a validation data set in a slide, in a couple slides. But basically, what validation means is to look at the accuracy and to look how well the model performed on some data that it's never seen before. That's the process of model validation. And then I already talked about model deployment. And then last but not least, we can talk about monitoring the model. Monitoring the model simply being to look at how well it's performing. We can look at some error metrics. Remember, for a regression model, some of those error metrics, I guess throw them in the chat. What are some error metrics that we looked at? Or let's go ahead and list all 4 of them. Oops. My email just pops up on its own for some reason. Let's go ahead and drop and put 1 each so that we don't have one person dropping all of them. If everyone wants to just drop one of them in the chat, go for it. Why is this happening? Sorry about that. All right, let me take a look at the chat. All right, so she said mean absolute error, perfect. Syntax error was an error inside of the code itself, I guess. These are error metrics that we use to see how well our machine learning model performed, if that makes sense. Such as mean absolute error, which is what Shri put.
So wait, I'm confused, but what do you mean? Like, what's the difference between the two?
So a syntax error or a value error or an undefined type error, those are all errors in the code itself. That means you've coded something incorrectly or you're trying to pass the wrong data type into the wrong area. What it means to monitor the model is to look at how well the model performed, I guess, to see like some sort of percentage, to see how off the model was from its predictions. Basically kind of telling how the model went. It's like getting a score on your test, if that makes sense. Yeah, great. Mean squared error, that's a perfect example. And yeah, a syntax error, yeah, as she said, it's a problem with your code, not a problem with the model. We have mean absolute error, mean squared error. There were 2 more. Yeah, Shri got root mean squared error, and then there was one more that didn't have anything to do with the mean, if you remember what we looked at. Not mean absolute squared. Remember, we square it just to turn all the values positive, or we take the absolute value to turn all of them positive. So you usually don't couple them together since they both achieve a similar purpose. But a hint is that this had to do with a percentage. It wasn't. It was a number, but it was a percentage. X% of the variation in the Y data is accounted for by variation in the X data. That's how we interpreted it. Yeah, R squared. R squared. Yeah, mean absolute percentage. I'm not sure if that actually exists, but that is a good guess. But yeah, R squared. If you guys remember what R squared was, and R squared was from 0 to 1, and 1 being all of the data was fit perfectly to the regression line, 0.8 being decent, right? It was the correlation or the correlation coefficient ranging from 0 to 1 or 0 to 100%, if you guys remember what that was. All right, cool. So those are some error metrics for a regression model. We'll look at some really cool ones for how to measure whether or not a neural network has performed well on the data.
Wait, I'm actually confused. What's the difference between validating the model and monitoring the model?
Yeah, so we'll hop into that later. There's actually a separate data set. I told you there was a training data set with labeled examples. I'll explain what a validation set is and a test set is in a couple slides. And then if that still doesn't make sense, let me know. But yeah, we're actually doing it right now. All right, so when we have a data set, what I said earlier about training is not the overall process. So sure, we have a training data set. Now the training data set is used to train the model parameters. The model parameters is something that we have no control over. This is the process of machine learning where we specify a model, but we don't actually tell it what math goes on inside of it. This is what's known as the black box of machine learning. The black box of machine learning means we have a data set, we throw it into a black box. We're not quite sure what happens inside. We have a rough idea of what the process is, but we don't know the exact numbers inside of it. And then we get spit out an output. And that's what the black box of machine learning means, is that we can't see inside of this box, this, I guess, metaphorical box of sorts. Now, not only do we have the training data, we also have the validation data and the test data. Now, this is something that is very, very crucial to understanding the process of machine learning, or rather deep learning in our case. So the validation data is used to determine what model hyperparameters to adjust. So let's say we're training our model. Let's say we have a data set of 100,000 images, or let's go down to 10,000 images. Now, from those 10,000 images, all of them are labeled, right? All of these 10,000 images are labeled for us. However, we split it into 8,000 training images, 10,000 validation images, and 10,000 testing images. Now, the reason we do that is because the validation data allows us to compare what our predictions were at the time of training. So this is oftentimes very difficult to understand, and to be honest, it is hard to explain as well. And that's because the validation data is what's used, I guess, to, I like to think of it as, what's a good way to put it? It's how, I guess, the model scolds itself for making an incorrect prediction of sorts. So the validation data is also fed in at the time of training. So the training and the validation data all happens during the training process. So the model learns from the training data, and then it tries to apply itself to the validation data. So basically, during the time of training, it looks at the validation data and it tries to see whether or not it was correct. So the training data is fed in with the labels, the validation data is fed without the labels, and it basically tries to compare its own predictions to the validation data. And this goes back to the process of iteration. We iteratively compare it to the validation data over and over again, and every time the validation data or the label of the validation data is different than the label of that it predicted, I guess, the model is basically scolded. It's said that, hey, you're doing bad. You're not doing very good. And that's what the validation data means, right? Think about what the word validation means. Validation, to like check yourself, right? to validate, to check whether or not a process was correct, or whether or not a process was true, or whether it happened correctly, right? So both of these processes are iteratively. We iteratively learn from the data, and then as we learn, the model tries to apply itself to the validation data, and then it compares its prediction, I guess, to the validation, the true label. And if not, it's scolded, and it's like, oh, you were bad. Try to change something in order to not be bad next time, right? Or you were good. It looks like you were able to pick up something in the image or something in the data set that led you to the correct answer. So this is a very, very important concept. Now we also have the test data. The test data, we actually feed it in with none of the labels. So let's say we have a data set of 10,000 images. What we do with the test data is that we just kind of set aside the labels, and we just don't look at them, I guess. So when Shreyas asked, so after we trained the model, Shreyas asked if can we look at unlabeled data? Yes, and that is your test data. So what we do is we actually kind of manually set aside the labels from the data set, if that makes sense. And hence it becomes unlabeled data, right? We don't, I guess we don't do anything other than just like not, we hide the labels from the model, from looking at the test data. And we treat it as completely unlabeled data. Our test data is completely unlabeled. And as a result, we tell the model that, hey, this is unlabeled data. Can show me what you got, I guess. Show me what you got. See how many of these you can get correct. And then once it's made its own predictions on the unlabeled data, we bring back those predictions or those labels that we initially hid from the model. And we just do simple things like looking at the accuracy. How many of the unlabeled predictions did the model make correctly, right? So that's what it means by looking at our final performance metric. And a final performance metric would be mean squared error, or RMSE, MAE, R squared for regression. And we'll look at regression today, but in the future, we'll look more at classification, which I think, in my opinion, it's a little bit more interesting, but that's my opinion, of course. All right. So let's take a look at what this means. This diagram might make it might make what I said in the last slide, it might make a little bit more sense. And Shri asked, is it used to check if the model is accurate? Yes. So the validation is checking whether or not the model is accurate during training, and the testing or the test set is used to detect whether the model is accurate after training, if that makes sense. So validation is during training, test set is after training. So after we've already packaged our model and we're trying to evaluate some sort of final model, I guess, final model error metric or of that sort. So if we have the labeled data set, right, 10,000 labeled images of some sort of disease, a common example is skin cancer. We have 10,000 images on whether or not a person, or whether or not a picture of some sort of, I guess, lesion on their skin, whether it's cancerous or whether it's not cancerous, right? There's only two options. So from those testing, from that labeled data, right, the doctor has already gone and labeled whether or not the lesion on the skin is cancerous or not cancerous. So we already know the answer, but we want to train a model to learn exactly, not how the doctor does it, but we want it to learn on its own. We want it to develop a process in order to detect whether or not a lesion is cancerous or not. We take that data set and we split it into three. Now, the vast majority is always reserved for the training data set, and oftentimes this is something that's up to you as the researcher, whether or not you want to split it into 70%, 15%, 15%, or 80, 10, 10, 60, 20, 20. This oftentimes comes up to you it's up to you as the researcher. These are just some common ratios, if that makes sense, that I've listed for you. These are some common ratios to start with, and then you can kind of fine tune it and adjust it from there. And you sort of develop an intuition for this the more you work on projects in this space. There isn't like, oh, for this data set, I'm going to use 82.5, 16.5, and whatever the remainder of that is. But they add up to 100. They all add up to the 100%, right? And this is something that you kind of play around with at the beginning, and then you get better at it as you go. Oftentimes, well, every time you want to reserve the most data for the training set, because that's how the model is learning, right? You want most of the data to go for the learning itself. Then we have the validation set, which is the scolding data set, right? It tells the model whether it's good or bad during training. And we want to also have a fair bit of data for that. So basically, the larger the data set, I guess the less you need for the training set, if that makes sense. Like if you have 100,000 images, you probably want to use 60-20-20, because 60% of 100,000 is probably good enough to learn from it. And then that way you have more data to validate and test on, if that makes sense. But yeah, we split it into 3 data sets. Sometimes we split it into 2, which we're going to do actually. It'll make it even more confusing, but just bear with me. We just split it into training and validation. And what we do is we pretend that the validation data set and the test set are the same thing, basically, which is what we'll be doing for convenience's sake. All right, so let's talk about what model overfitting means. So let's first talk about what do you think noise means, I guess, in terms of data? What does that kind of sound like to you? What do you think noise means?
Data you
A
don't
lot of
need.
things going on. Oh.
Yeah. Yeah, a lot of things going on. That's a good answer. Shreyas, what were you going to say?
Sorry, data you don't need.
Data you don't need, also a good answer. Actually, a combination of those answers would be what I would say is correct. Noise on the data set, not quite variables, Shri, or I don't know what you meant exactly by variables, but yeah, so Noah's correct, and there's a lot of things going on, and those lot of things that are going on are data you don't need, or I guess data that's like distracting, I guess. It's a lot of it's like, I don't know how else to describe it. I guess like wiggling back and forth from what it is. It is just simply called noise. Yeah, Shri said outlying data. That's a good way to put it. However, it's not data that we want to remove. So Shreyas's answer was kind of sort of correct. Or kind of sort of incorrect in terms of that it's data that you do need it, but there's a lot going on with it, and hence it tries to throw the model off of sorts, or it tries to distract from the overall goal of the model. So the overall goal is to create something that can predict on data that it's never seen before, right? That's actually the goal of every person that works in the artificial intelligence space or around the world, is they want to create a model that is able to generalize on real world data, right? Generalize on data that it's never seen before. It's very easy, or not very easy. It's easier to train a model in a lab or on a computer. But what we want it to do is look at data that it's never seen before. And noise distracts us from achieving this purpose. So what it results in is low error on the training sets, right? So the model is able to train very well. However, there's a high error on testing and validation sets. And you can kind of see what overfitting means in this diagram before, right? Our optimal thing is to gather this trend, right? This almost like a frowny face trend in our data, right? But overfitting, okay, overfitting has a 100% accuracy, right? It hit every single one of these data points, but is this model good at looking at data that it's never seen before? No, it's going to be completely horrible because it did not pick up on the trend at all. It's what known as overfitting. It basically just achieved 100% accuracy, but it sucks on testing and validation data sets. It's absolutely horrible because it'll never be able to predict on a data point that it's never seen before, or if it does, it's just simply not going to be very good. And let's see why this is an issue. And I'm just going to, I guess I'll just annotate on my screen here. I think there's a Zoom annotation tool. Let's try this out. There we go. All right, so I'm just going to draw a little example. All right, so let's say we have that's not a very straight line, but this is an X and Y plane. And let's say we have the same data. Can I draw shapes? I cannot draw shapes, so bear with my mouse drawing skills. This is gonna be a struggle. All right, so we have this data. Oh God, let me use my trackpad. That's probably easier. Okay, what sort of data or general trend does this look like to you guys?
A positive linear trend.
Yeah, great. A positive linear trend. So can I change the color on this? Oh, someone drew on someone drew on the thing. But yeah, let's say we have a positive linear trend, right? So what we can do is, can I change the color? Yeah, I can. Great.
Oh.
Okay. So a regression model would simply predict something like this, right? Very, very good, because this line can go further and further, right? This line can go further and further. So if we have unlabeled data, let's say we had unlabeled data all the way up here, it might be still pretty decent, I guess. It might be pretty decent. Let's say we had unlabeled data, even down here we had unlabeled data being blue data, right? It picks up the general trend of what we're trying to achieve, right? However, let's look at something that has overfit with, let me do, what's a good color? I'll do, yeah, yellow is fine. Okay, now let's take a look at this. Now this is, quite frankly, it's horrible, right? Even for these blue points that were down here, look how far away this blue point is from what the model thought it was. This vertical line that I've just drawn is the error of the model right here. This thick line that I've drawn is how far the model was away from its prediction. Otherwise, it was pretty close to the red line, but it was just absolutely terrible from this yellow line. This is what overfitting means, is that it sucks at data that it's never seen before, even though it was 100% accurate on those green points. So this is something that's very important to understand, because I see people all the time showing up to science fair. I have 99% accuracy on this. I have 100% accuracy on this. Well, obviously you do, because you just overfit your model. It's easy to overfit your model. It's like having the answer key to the test like a day before, and you simply just memorize the answers in the order without learning any of the concepts, right? That's just, it's almost like cheating. You can imagine it like cheating. And now like don't even ask like what these blue points are going to yield. Like I have literally no idea what's going to happen with these over there. It's not going to get anything at all. So does overfitting make sense? I'll run a poll. This is something that people do not understand. Everyone tries to do deep learning projects, yet no one understands very basic ideas such as overfitting. There's also underfitting, by the way, which we're going to do next.
Yeah, it makes sense.
Okay, cool.
Yeah.
And you can see why so many people show up to competitions, and even people publish research thinking that they have 99% accuracy or 100% accuracy. Well, obviously you do. The model is easily able to just connect the dots, right? It can connect the dots, but can it connect the dots with data or with dots that it's never seen before? Probably not. Or actually, yeah, most likely not. So yeah, we have a good number of thumbs up. Yeah, now is a good time to ask questions while I get rid of this. All right. Yeah, and so Shri actually said noise is the distortion in the data. Very interestingly, what the Google definition means, sometimes you actually want to add distortion to the data, or you want to add noise into the data in order to make it better at looking at real world data, right? Because real world data is never perfect. And sometimes when you have a perfect, you have a perfect data set, sometimes researchers purposely add noise to their data set in order to make it better at looking at unlabeled data, if that makes sense. So that's what that Google definition means. Noise is a distortion in the data. Because sometimes you manually add noise, which is an interesting concept. Arush asks, how exactly do people overfit their model? That's a very good question. People, usually overfitting happens when your model is overly complex, or if you've used, as I mentioned earlier, deep learning for a problem that didn't need deep learning, right? So if we were to use deep learning on the positive linear data that I drew, it would overfit. That deep learning would create that yellow line that I drew, because deep learning, or at least a deep learning model that is overfitting would have done something like that, when we could have simply created a scikit-learn regression model, right? A simple linear regression model. And that would have been much better for the task, or better suited for the task. And it is unlikely to overfit. So it's better to try machine learning first, unless you know that you have a very complex task, then you do need deep learning. But also, overfitting is something that can be quantified with plotting the error from our test and validation data sets versus our training set. And we're going to look at that in a second. So I've given you half the answer, and I will continue the answer to that question in a couple slides. All right. So let's look at underfitting. Underfitting means that the model doesn't capture the trend in the data. If we're looking at the data, which was quite obviously, there's like a little frowny face, right? It is going positively linearly at first, but then it's clearly dipping down, right? And what is that, like a downward facing parabola or whatever, if you guys have learned that in math yet. You will learn it in algebra too if you haven't already. Yeah, but it's often the result of an excessively simple model, right? If you tried to use regression to fit on this data, right, it wouldn't be the best in this case, right? It's overly simple. It's not capturing the real trend in the data. And yeah, that's what overfitting means. So let's take a look at this. And I want to pause here for a second while you guys really soak this in as to what underfitting, overfitting, and what an optimal line looks like. Yeah, Shri said a quadratic regression would work, or what if you ran a quadratic regression? In this case, yes, that would probably be the best type of machine learning model to run on this data set. Just this example that I took a screenshot from on Google. But yes, underfitting is like actually trying to use a linear model. That would probably underfit, and using like a deep learning model or like an artificial neural network would probably overfit with many layers. But yeah, hopefully this concept makes sense. Underfitting and overfitting would just absolutely suck at looking at unlabeled data, right? Because they simply don't capture the trend in both cases. However, overfitting captures too much of the trend, if that makes sense. Like it literally connects the dots from point to point, and underfitting doesn't capture enough of the trend. And optimal captures the rough trend, but if you see, it doesn't run through every point, but it gets the gist. It gets the gist of the data set. All right, so let's look at what a good model looks like. Actually, I'm not even sure if we'll have time to hop into code, but no worries. Hopefully the slides are interesting in themselves. But this is very important even to just understand the conceptual behind it. It's easy to write the code, especially because there's so much code online that you can simply copy from. Few people, and even fewer people at your guys' age, actually understand what's going on. I would say there's like a handful of students really that actually understand what's going on. And I think all of you are all of you going into AST 9th grade? I think all 5 of you are. I might be mistaken, but yeah, cool. You guys have a very big head start. I did not know this stuff until the end of 10th grade. But yeah, let's look at what a good model. Oh, Shri is 1 year younger. Nice. You're even one more step ahead. But let's look at what a good model what a good model looks like. So a good model, what we would want to plot is error versus training time. So why it says epochs there, some people pronounce it as epochs. I don't know how it's actually pronounced, but I pronounce it as epochs. If you watch YouTube tutorials, some people say epochs, but some people do say epochs. Don't be confused. An epoch is a period of time, right? I guess, where have you seen that in class? Like when you're studying like the dinosaur ages or whatever. I don't know. Like an epoch is like a period of time, like an era or like a period. I guess like the Jurassic period or whatever. That's an epoch. It's just a period of time. However, in our case, an epoch is one iteration through the data set. So it is related to time, because the more times you go through the data set, right, the longer it's going to take to train the model. So you can just imagine this is time, and this y-axis is error. So ideally, when you're training a model, you want it to get better, right? You want the model to learn over time, and hence you want the model to make less errors over time. So less errors over time is meaning that we're going to start out with a high error at the very beginning amount of time. And then as we train the model, it's going to exponentially increase. And what we want is almost a J-shaped curve of sorts. Wait, a J is facing the other way. I guess a backwards facing J in our case. But yeah, this is what a good model looks like. However, if we were thinking about overfitting would still create this line. Overfitting would still show you that you have 0 errors, right? Or you're approaching 0 errors. But that's pretty misleading. So what we want to do is check our performance against the test set. The test set, again, is unlabeled data. What we want is the test set and the training set to perform very, very similarly, which is what's called optimally fitting, right? An optimal curve. An optimal curve means the test set and the training set display very similar behavior between each other. And what?
So training set is points that are labeled that it is basically overfitting, and test set is points that aren't labeled, correct?
Yes. So the training set, it's not overfitting on the training. Well, it could overfit on the training set. It's just fitting the training set.
But it's already labeled data, right?
Yeah, exactly. Okay. So we're just learning from the training set, or we're kind of learning how to learn from the training set, if that makes sense. And then we're applying this knowledge of how we've learned how to learn, and we're applying that to the test set. And the test set is unlabeled data. And the unlabeled data should display a similar pattern of sorts. And this would be a very, very good model, because it's not overfitting or underfitting. It's just right. Yes, she said the more epochs, the more the model improves. Ideally, yes, right? Sometimes no. This is what you ideally want to happen. This is a good model. So let's look at a model that is not good. This is what overfitting looks like on an error graph. So the training set is doing great. The training set is still showing that it's approaching 0 error. It's approaching no mistakes on the training set. However, the test set has just gone out of the window, right? It's just around this point over here, around this yellow point over here, it started to be bad, because what's happened is that it's overfit. This is where the model recognized that it's overfit. So when it's looking at unlabeled data, well, it now sucks. So it started out with a similar trend, but that similar trend is kind of irrelevant, right? Because the similar trend was on very high error. But the moment we started getting to lower error, the test set just started being bad. And hence this model is what's known as overfitting. This model is overfitting because, well, simply the model could not generalize well to unlabeled data. The error actually started increasing. And this is what overfitting looks like. Ideally, what we would want to do is locate the point where they kind of intersect, or where they were the lowest and about the same, and we would want to just stop training here. And we'll learn how to stop training early using something called early stopping in order to prohibit our model from overfitting. So maybe it's a good trend, it's a good trend, it's a good trend. We approach this yellow area. It's still a decent trend, and right before it starts overfitting, we just say we just stop the model basically. And as a result, we have a pretty decent model because it's still picked up on a good trend here, but then the bad trend started being the more we train. So Shri said the more epochs, the more your model improves. Not necessarily. Ideally, that's what you want to happen, but not necessarily, right? This is an example of overfitting where the model gets worse the more that you train. So I hope this makes sense. We looked at a visual example of what overfitting looks like on the last slide, and this is what I guess it looks quantitatively inside of our error metric. Yes, we're going to learn when we recognize when we should stop our training. Actually, you should stop training inside of this yellow line. I guess that is recognizing when we should stop our training. And we're also going to learn how to tell our neural network to stop by itself when it starts to overfit, which is pretty cool. All right, so let's hop into a mini lesson about biology. And again, you know how I said it was like 10 to 11:30/12? That's because I prepared like 90 slides, and we're about 30 in, and it's like I've prepared all the content, and we're just going to get to wherever we get at some point in time. I'll find a good stopping point somewhere between 11:30 and 12. But yeah, sorry if you have like a hard deadline between that time period where you have to leave, but you'll have the recordings. But yeah, let's just hop into what you know about neurons. Feel free to unmute or drop it into the chat. And you don't even have to like say what a neuron is, just what is it associated with, what is its function, what type of class have you maybe looked at it before, just thought bomb it, anything you know about it.
They send messages by electrical impulses and are mainly like used in like with the brain, and like the brain trying to communicate and tell other body parts to do something.
Yeah, exactly. That is a very good answer. And yeah, so Shri said they're like cells that transmit information, similar to Shreyas's answer, by electric pulses. Great. The electric pulses part is a little bit redundant when we're looking at a mathematical neuron, but the idea that it transmits information is important. I guess what is the I don't know how to say it without giving away the answer, but what do neurons make up, I guess? What is it called inside of our body?
Oh, yeah, neural network.
Shri said neural network. Not quite. We don't have a neural network. It's not called a neural. What?
Nervous system?
Yeah, the nervous system, or the central nervous system, yeah. Right? That connects mainly, it's your brain to your spine, but the neurons do go to the rest of your body, right? The largest clusters of neurons are in your brain and your spine, right? That's why when you have a spine injury, you can get paralyzed because, well, it messes with your central nervous system. So yeah, that is the biological definition. That was an aside. The paralyzation had nothing to do with I don't know why I said that. All right. But yeah, let's look at what a biological neuron looks like. This is what's known as cell staining. I'm not a biology or chemistry guy, so don't ask me how staining works, please. I have no clue. But this is where I think you like put the cell on like a slide, and then you put some sort of like ink or some sort of liquid in it, so that when you shine a light on it, you can see it easily. I think that's how it works. I'm really just guessing, to be honest. But here's what a biological neuron looks like. It's this central area here, which is like the central apparatus, or like the nucleus of a cell, right? And then we have these little like tendrils, like octopus tentacle looking things that come out of it, right? They're just branching out. And that's what's sending all the impulses. They're not only sending impulses, right? The word that Shri used, transmit, is a very good thing, because not only do they send impulses, but they also receive impulses, right? Like when we touch something, when we I don't know, like feel a hot stove, we get that electric pulse to tell us not to do that anymore. Like so on and so forth, pain, et cetera, et cetera. But yeah, that's the function of a biological neuron. All right. So let's move to the next slide. Let's look at a little like artistic rendition, I guess, of what a neuron looks like. Let me open the chat 1 second. Sorry. All right. Yeah, let's look at what a biological neuron is. So, a biological neuron, in this I guess drawing, or whatever computer has drawing of it, right? We have our nucleus. We have what's known as these axons and dendrites. Ignore everything else. It's pretty redundant for when we're looking at a mathematical neuron. Just look at this axon and these dendrites, right? These dendrites are these little tendrils that branch out, and they basically, when they're touched, or when some sort of impulse is sent, they send that to the nucleus, and yeah, whatever, the axon. The axon transmits some sort of pulse into whatever this green thing is. I'm not really sure, to be honest. I just snapped this picture from the internet, but this green thing is probably going to do something with that information, right? When we accidentally touch a hot stove, right, we immediately pull our hand back, right, because of the electrical impulses, because the neuron has transmitted some sort of impulse to our brain, and hence to our muscle. The brain transmits some sort of thing to our muscles in order to contract them and pull our arm back, right? So we can simply boil this down into is a simplified neuron model. I actually took this from a deep learning course that I took online, where he really simplified this down into just a 3-step process. We have our dendrites that are taking in an input. They're passing it into the nucleus, which does something. It doesn't really matter what it's doing for our purposes. And what it does is it spits out an output. This axon is going to take the question marks and spit it out to something to the right of this. And as a result, the output is something that can be taken into consideration. Whether it's, I guess it's just simply input going into something in the middle, going into output. Dendrites going into nucleus, going into axon. And that's input to output, right? An input to output is, I guess, what in math takes an input and spits out an output? What in math? Tree said XY, yeah. Let's get a little bit more specific than that. But that is the right answer.
On the tip of my tongue.
Shamal said formula, good answer. Even it also starts with an F. What?
Linear functions?
Yeah, or just functions in general, right? And any sort of functions, just f of x, right? Linear function means like mx plus b, right? That's a linear function. But I mean, x squared is also a function, right? It's also taking an input and an output. Shri said xy. That is a good answer, because it's just we change x, and it doesn't really matter what x the formula for x is, right? It could be x to the 1,000,000th divided by 900 times 4 minus 2, right? It's just some sort of function. And as a result, y changes, or as a result, f of x changes, right? F of x changes. So in our case, these question marks can actually be looked at like f of x. This nucleus can be looked at some sort of function, and it doesn't matter what the function is. And the reason that it doesn't matter what the function is because the neural network, right? Artificial intelligence, it learns, right? Its purpose is to learn. And artificial intelligence actually creates its own function. And that's kind of mind-boggling. We don't tell it what the function is, but it creates a function on its own. And that's the creepy part of machine learning, or rather, in my opinion, it's the fascinating part about machine learning, is that it creates its own function. It creates its own sort of thing that happens between the input and the output, and we don't really know what that is, or we don't know what that is exactly. So let's look at what a mathematical neuron is now. So I guess this is a good stopping point. I'm gonna grab some water. We'll take like a 5-minute or a 3-minute breather, and yeah, I guess we'll just pause for a second and then move on with what a mathematical neuron is. So I'll be right back. All right, I am back. Are we good to go? Yeah, I start losing my voice when I talk for too long, so I grab some water. You're good? All right, cool. I'll run a reactions to make sure everyone's back, because I did just leave for an unspecified amount of time. All right, I dropped a poll to see if you're ready to move on. All right, waiting on Arush and Chiamal. All right, we are good to go. All right, so if you remember what we were just looking at, right? We were just looking at inputs going into outputs, and we just came up with the answer that a formula or a function, right, more specifically x to y, is basically taking an input, passing it into some formula, and spitting out y or an output, right? So this is what models down into what's known as a mathematical neuron model. And we call these perceptrons. So it's a, I don't know, it's a cool sounding word. But what a perceptron is it's simply a neural network unit. It's called an artificial neuron. An artificial neuron meaning something that's computationally designed. And a perceptron, it's actually been along for a long time. It's been around since, I think, the 1950s or 60s. And someone created this computational neuron, or an artificial neuron, called a perceptron. And a perceptron simply looks like a neuron, right? It looks just like what we had in the previous drawing, where we're passing in some sort of input, And these are like the dendrites, right? It's passing it into this nucleus, and then it's spitting it out in the output, which will get carried by the axon to our cells or our muscles or our central nervous system. I'm not a biology expert, but yeah, I think you get the idea of it. But here we have X1 and X2. This is arbitrarily chosen. By the way, you can have any number of X's that you want. You can have any number of inputs that you want, and you can have any number of outputs that you want. Yeah, this is just a single perceptron taking in two inputs. So let's say we had a perceptron that's purpose was to sum all its inputs. What would our formula look like?
Adding all the x's together.
Yeah, so it would be x1 plus x2 plus x3 all the way to x of n, right? Where n is the stopping point of our variable. And in this case, we just have x1 and x2, so we're just f of x would equal x1 plus x2, right? So y would equal x1 plus x2. However, our perceptrons for our neural networks are a little bit more complex. So remember when I talked about training and how the model develops its own sort of function, right? It's its own sort of intuition as to what the function should be in order to achieve the best results of sorts. So what we need inside of our perceptron is the ability to adjust some sort of parameter in order to make this change a possibility. So x1 and x2 are they can't be adjusted, right? That's our input data. You can't just change the input data in order to achieve better results. That's like cheating. You can't just change what you're passing in order to get what you want, right? So what we do is we want some parameter that can be adjusted, allowing our model to learn, I guess. So what we do is what's known as this weight parameter. Let me adjust this slide really quick. This should be times weight 1 and times weight 2 in order to make this make a little bit more sense. All right, so times weight 1 and times weight 2. Now, in the beginning, these weights, weight is basically, you can imagine it like an importance that you give to each of these inputs. So let's say we have an, I guess let's take a very, very simple example. Let's go back to our example of just adding. Let's say x1 was equal to 10,000, and let's say x2 was equal to 0.5. So I guess what's the result of that? What's our summation going to give us? What's f of x going to equal? If we have x1 equal to 10,000 and x2 equal to 0.5.
10,000.5?
Yeah, 10,000.5. So in the grand scheme of things, did the 0.5 really even matter? Like, did it play a significant role at all to anything of our output, right? 10,000 plus 0.5 equals 10,000 plus, or 10,000.5. But in the output, I mean, the 0.5 played little to no role. And hence, we can think of this as having a higher weight or a higher importance to the overall output, right? So the weight given to that would be far higher. We would multiply this by something much smaller in order to balance our inputs. So what we would want to do is multiply this by a teeny tiny weight and multiply x2 by a very massive weight in order to give them the same importance, right? Because even though that the answer is 10,000.5, 10,000 and 0.5 are both numbers, and we want them to have an equal say in the final output. So it's kind of counterintuitive that you multiply x1 by a small weight and you multiply x2 by a very large weight in order to give them an equal importance, if that makes sense. But yeah, what would our f of x be now, I guess? What would our f of x be now? Formulaically.
X of n times w of n plus, or x of 1 plus w of 1 or x of 1 times w of 1 plus x of 2 times w of 2, and so on and so forth, is like adding each pair together to equal the output?
Yeah, perfect. That is exactly what it is. And this is what a perceptron is. It's simply just multiplying a weight and with the input data. It's just multiplying the weight with an input data, and each of these weights can be different. So weight 1 can be different than weight 2 because each input has a different importance. Each input has a different weight that you assign to it, allowing our model to learn. So in the process of training, all that's happening is adjusting the weight. So it's weird to think about that we can learn how to detect whether a cat is a cat or a dog is a dog with a computer simply by adjusting weights inside of our perceptron model or inside of our artificial neuron that we've created. So this is what's really going on behind the scenes. However, what happens if x is 0? Mathematically, what happens?
It doesn't impact the set.
Yeah, it doesn't impact it at all, right? If x was 0, even though we multiply it by a weight, right? 0 times any weight, whatever the weight is just still 0. But 0 is still important in our data set. We don't want to just like not consider 0, if that makes sense. You do need to consider 0. And yeah, I mean, there's not much to it. You have to consider 0. So what we do is oh yeah, this is the correct answer to what Shreyas had, x1 times w1 plus x2 times w2. And w1 and w2 are what's called weights. So yeah, what happens when x is 0? Okay, I got ahead of myself, but yeah, what we need to do is add a bias term b. So no, I spoiled the answer, alas. Let's modify this. Let's change this to times. And this is something, by the way, that few people are really understanding. When I present at science fair, I simply just grab a scratch sheet of paper and like show the judges like what is going on behind the scenes, and then they're like, wow, you actually like know what's going on. And honestly, I don't think it's even that hard to understand. It's just that people don't understand it, and I find that very strange. I feel like when you want to learn something, you should learn from the ground up rather than just trying to write the code behind it. But yeah, if x is 1, as I just said, we need to add some sort of bias to it, right? And the bias is simply allows us to be non-zero. A bias is just some sort of constant. And hence our model looks like this. W equals x1 w1 plus b plus x2 w2 plus b. So if we were to have one input, what does this look like to you in algebra? This should look like something very similar that you've seen before. If we were to cover up x2 stuff, if we just had x1.
X equals fx plus b? No.
Yeah, or well, y equals mx
y
plus
equals
b.
X,
Yeah.
mx plus b.
Yeah, with m being what?
W1.
Or like in math, what is m?
The slope?
Yeah, the slope.
Yeah,
and then
slope.
what is b?
B is y-intercept.
Yeah, b is y-intercept, right? So it's strange how a neural network is almost boiled down to something that looks very analogous to our simple point slope formula, right? Y equals mx plus b. However, this m, or this slope, is something that can be adjusted depending on the example. So this is what a perceptron or an artificial neuron is. It's just a bunch of x1 times w1 plus b, and it just sums all of these up to achieve some sort of output. And I find that it was hard for me to wrap my head around how all of this randomness is just boiled down to inputs going into outputs, where all that's being changed is these weights and biases. That's all the model is doing.
can the bias change between X values, or is it one constant bias?
It changes between X values. It adjusts the weight and the bias. That's something a little bit harder to understand. It's what you have to do is X1 times W1 has to overcome the bias in order to make an impact, if that makes sense. Like X1 and W1 have to be larger than the bias in order to make an impact. And that's why weights and biases can be negative. Yeah, it's a little strange to think about, but I think the only way to understand that is when you start writing them in code, to be honest. Yeah. And you can see how this was y equals mx plus b. That's just two-dimensional, right? But the minute we add in more input data, it gets into more than two-dimensional, right? And as a result, the human cannot imagine a neural network and all this multi-dimensional or n-dimensional data. So we have a couple more slides, and I think that's a good stopping point. I apologize for not doing any code today, but we will start with the code next time. Yeah, we'll just start with the code next time. It's no big deal. Let's first look at one of the quotes that I set out. Another key point to think about. A single perceptron is not good enough for complex systems. We need to create a multi-layer perceptron, which is called an MLP model. A multi-layer perceptron means taking one of those neurons and, well, not taking one of them, is to create numerous perceptrons inside of a model. And now, if you've ever taken a picture of what a neural network icon looks like, this might be something that looks familiar to you. Now, this is simply just many perceptrons right next to each other. I don't know why this image isn't centered. Let me fix that really quick.
Can you go back to the previous one?
Yeah, I'll go back.
Slide. Thank you.
So yeah, a single perceptron is not complicated enough in order to go through it. She asked, what are all the layers? We will go through all of the possible layers in an artificial, or not all of them, but the most popular ones. Not today, but next time. Let me know when you're good.
Oh yeah, I'm good, thanks.
All right, awesome. So here we have a multi-layer perceptron model. So again, remember our example of how we had the input going into the question marks, going into the output. Those question marks can be called the hidden layers or the black box. And the hidden layers, although they sound very, very mysterious, right? We will actually, as the deep learning researcher, you do say what the hidden layers are. However, you don't explicitly understand what's going on inside of them. You don't explicitly understand what the weights and what the biases are inside of them very specifically. So a multi-layer perceptron model is the basis of a neural network, right? It's a perceptron, again, is an artificial neuron. So I'm going to stop calling them perceptrons, and I'm just going to call them neurons from now on. You can imagine them very similarly. Perceptron is the formal term for them. It's the term for an artificial neuron. But here we have just a bunch of neurons. We have the input neurons, right? The input neurons take in our input data over here, and they're densely connected to a hidden layer. What dense connection means is that every one of these input neurons is connected to a hidden layer, right? So this input neuron at the top left, it's connected to 1, 2, 3 things, right? That's what a dense connection means. It means that the input neuron or the previous neuron is connected to every single neuron of the next layer. So each layer is each vertical column, I guess. We have the input layer, then we have the hidden layer, and then we have the output layer. What did I say made a deep learning network, or what did I say made a neural network deep? This was at the very beginning of the lecture, the first quote that I had.
The layers. A lot of hidden layers.
Yeah, a lot of hidden layers, or actually anything that's 2 or more hidden layers makes it a deep learning model. So this is a multi-layer perceptron, but if it has 2 or more hidden layers, then it is a deep neural network. And that's deep simply refers to 2 or more hidden layers. And we'll learn what types of hidden layers we could possibly have. All right, so hopefully the multi-layer perceptron model works. And each of these circles is simply it's its own perceptron. This entire thing, x1, x2, and output, this entire thing is one of these circles, by the way. Yeah. So this single circle contains inputs, it contains a function with weights and biases, and it contains an output. And as a result, the output of the input layer turns into the input of the hidden layer, right? The output of the previous layer turns into the input of the following layer. And that's what's called a feed-forward neural network. And that's just basically meaning that whatever is in the previous layer, whatever the previous layer outputs, it's just fed forward into the following layer. That's all it means. Yeah, great answer, Noah, where we have multiple hidden layers, right? Here's a simple neural network. And what term did I use when I said each of the previous layers was connected to the output layers? What is that called? It is blank connected. It's an adverb, I guess. That's probably not super clear, but that was a bad question. It's densely connected, referring to the previous slide. Densely connected, again, meaning that every one of these neurons, interconnected. It's like a web, but it's just densely connected. And there's one of the hidden layers is called a dense layer. And that's Shri asked, what are all the layers? One of the types of layers, which you already know now, is called a dense layer. So in our simple neural network, we simply have one of these hidden layers. However, the models that we're going to be creating are deep learning neural networks, and they have numerous hidden layers. And imagine trying to look at the weights and biases of these. Can you do that? Like, I would not want to do that, right? Tracking every single one of these lines, right? That's just stupid. And this is a deep learning model, but usually we have 64 or 128 or like multiples of 2, or powers of 2, but they get pretty high. And yeah, that's not fun, right? The model, just let it do its thing, and it will deal with the math in the middle. Our job is to just create the model. It's to define what these layers are, and these connections the weights and biases will be determined by the model itself. And yeah, that's the essence behind what a deep neural network is. We can quickly go over regression models, and then we'll stop. It's just 2 or 3 slides because we'll start the lesson off next time with hopping into a Colab notebook and making a regression, using regression data, or creating a regression model with a neural network. So for this course, there are 2 types of regression, or 2 types of models. There's regression models and classification models. Regression models deal with continuous data, right? Like our scatter plot data. It's X versus Y data. And it differs from categorical data, such as classification, right? Categorical data means you're specifying a category for it. Like, let's say we had a data set of animals. Each classification would be the type of animal, right? Giraffe, horse, cat, dog, pig, whatever. And luckily, even though we're dealing with neural networks, we'll be able to quantify its error using values we're already familiar with, such as mean absolute error, mean squared error, RMSE, and R squared, so on and so forth. And yeah, I think this is a very good stopping point. All right, yeah, next time we will get into the walkthrough project, which should be pretty short, I would say.
Could you go to the previous slide?
Yep. And yeah, now is a good time to ask questions since we're right in that good point. And if what I can do is I can flip through all of the slides if that helps you spur, or if you want to take a look at notes, whoever was taking notes, to see what is looking a little bit confusing, because in this course, unfortunately, if you like miss one, you do like you have to catch up with the YouTube recording or something, because otherwise you simply will be just completely confused the next time we go into this. All of the knowledge of deep learning builds upon each other, like very, very, very hard. Like every topic is interconnected. So yes, I can explain what types of data regression models can predict. So in our case, let's just think of a couple examples that we've actually already worked with. Regression model is we can simply think of it like linear regression. So one of the examples that we had in the slides for Python for Research was ice cream sales versus temperature, right? As temperature increased, ice cream sales went up. A regression model would be able to predict that. Similarly, what's another thing? We have the diamonds data set. So as the type of cut went up, or I guess as the carat went up, the price went up of the diamonds data set. What else did we have? We had height versus weight. As a person was heavier, they were more likely to be taller. What else? There was another one. Does anyone remember what it was? Height versus weight was the homework. What was that lesson about? I'm forgetting.
Was it TV?
Yeah, it was the TV ads. Yeah. It was the types of ads versus sales. Yeah, that's exactly right. More specifically, the TV ads had a great regression for it. And actually, in ours, we're going to do like, you remember how we did multivariable regression with newspaper ads, TV ads, and radio ads? And that was multivariable regression because there were 3 different variables, yet they were predicting one thing, right? So we're actually going to create a neural network that can predict house prices. And as a result, the model will be taking in square footage. It'll be taking in lot size. It will be taking in like the month that it was on the market and the year that it was on the market. It's not only going to be 3 things, but we're going to perform a neural network that creates a regression model on I think 19 things. Yeah, so it'll be pretty cool.
Can you go to the previous slide?
Yeah, sure. She said for the height and weight data set, the model had 85, but you tried NBA players to see how it would work, and it was kind of bad. What was the types of stuff inside of the NBA players data set? Like, what was it measuring? Like height and weight of NBA players, or points, or what? Do you need me to go even further back?
No, actually, what what is a classification model?
We'll cover that next time. It's just basically like if you imagine you have a data set of pictures of animals, it's just classifying them as to what type of animal they are.
This is not like classifying numerical data.
No, there are 2 types of models, and the first type that we'll explore is regression, and then we'll go into classification tomorrow as well afterwards.
Classification has the capability of analyzing photos and like things like that.
Yeah, and not only photos, like let's say we have so we're going to go into an example of breast cancer data, and it's not an image of breast cancer. It's going to be like I think it's like the radius of the breast cancer, or the diameter, and the smoothness or something. I don't know. There were like a lot of features, and it classifies it as to, based on this numeric data, whether or not it thinks that there's breast cancer or not, if that makes sense.
Oh.
So even though it's not an image, it's like a bunch of measurements, and it's still classifying it. And we'll learn about encoding, label encoding, and one-hot encoding. Just super interesting stuff with classification. All my research has been with making classification models for medical data.
That's really cool.
Yeah, no problem. Shri said it was the data set. You inputted the weights of NBA players, and the heights were not very close. Were they too low or too high? Out of curiosity, too low, right? That's interesting because NBA players, well, it's because they're abnormally tall, right? So yeah, so that's why the model was bad. NBA players is a very weird subset of the data, right? NBA players are not the general population. people of that height generally don't weigh the same as the normal population, right? They're absurdly tall. So it's actually pretty cool that you tried that. You should expect for the model not to be very good because NBA players are not representative of the general population. Yeah, there's no one that's 7'2", right? In our data set, there were probably maybe 1 or 2 people tops that were 7'2". And that's why the closest thing to it was 6'8", and it thought Shaq was 6'8", even though he is far from it. He is 6 inches taller than 6'8". It's cool that you tried that, but I hope that makes sense. Yeah. All right, I'm gonna flip through these slides, and I'll just start right from the top, and just pause me when you have a question about anything, and if we're all good, it'll be good just to take another little peek at all of the slides because we covered a ton of theoretical stuff today. A ton of theoretical stuff. All right, so we covered the definition of AI, ML, and deep learning. Just unmute and just say stop, I want to cover that if you have a question. We covered what machine learning means, what neural networks or deep learning means. We covered, deep learning. We covered supervised versus unsupervised learning. We'll be focusing on supervised learning in our case. We learned about the pipeline of the model, which I think it'll make more sense once we start getting into the code. But I hope you understand what the training process now means. And data preparation is something that we did in Python for research. So you should be familiar with that. And then we skipped some of these steps in the middle, which we'll come back to. But I hope monitoring the model with error and with those metrics makes sense. Splitting the data set, I hope these types of data make sense, what a training set is, what a validation set is, and what a test set is. Although this might be confusing, definitely. In my opinion, it's pretty confusing. But yeah.
Could you explain the difference again between the validation data set and the test data?
Yeah, so the validation data is actually something that is in the process of training. So while the model is training, we use validation data to kind of scold the model, basically. So what we do is validation data is also unlabeled, or it is labeled, but we hide the labels from the model. And while we're training, we try to kind of fit to these unlabeled examples. So this is all during training. Validation data is during training. And during the training, we try to fit on this unlabeled data and see whether or not the model is able to do it. If the model is able to do it, then okay, our weights and biases must be good. If the model is not able to do it, then the validation data is what really drives the process of hey, you kind of suck at looking at this type of data. Go ahead and update your weights and biases to see if you can do better next time, if that makes sense. So hopefully the connection between weights and biases and validation data is kind of making sense now because it was introduced as 2 separate things, but that's what's happening. And then the test data is after we're done training. So after we're done training, we have a fully packaged model. If we take a look back at our pipeline, we have a packaged model, which is done. This is a bad word. It should be test model instead of validate model. Validation happens during training. But yeah, we test our model after we've packaged it, and we basically see how good it is based on unlabeled test data, if that makes sense. So test data is after the fact. Is that a little bit more clear?
So wait, the validation data is during training.
Yes, the validation is during training, but validation data and test data are both they're both unlabeled, if that makes sense. It's basically we're training the model a little bit and then we're quickly testing it against the validation data. It's like a checkpoint in a video game. It's like a little checkpoint that we're making against the validation data over and over again. And we're using that checkpoint to update our weights and biases and then train again. And then we check against the validation data and then we update our weights and biases and we train again. Then we look at the validation data, update the biases and weights, so on and so forth. We keep doing that, and that's what training means, is to train using the training data. We look at the validation data, and if the training was good, then we keep the weights and the biases the same. If the training was bad, then we update the weights and biases and then go back into the training process. And that's what the epochs are. It's iterations through our data set. basically the more you train it. And
So
then
wait,
yeah.
so the testing, so validation data and training data, so they occur during the training model phase, right?
Yes.
But so then validate model is really, so now I'm confused what happens there.
That's what the test data means. The test data is like after we're already done. It's kind of a bad keyword. Just replace validate model with test model, and it'll make more sense, I think. This is where the testing data comes into play. It's after we've already trained the model. The test data and the validation data are they're doing the same thing, except the validation model is the validation data is during the process of training. It's like we're testing the model or we're validating the model during the training process, but the test data is after the fact. It's like real world data, basically.
Okay.
Yeah. And I'm going to keep re-explaining this every time we write it in code, because I started to understand it once and then it got confusing again, and then I wrote it in code and then it got confusing again. And it's something that I think you'll understand a little bit more the more we work with it. It is very, very confusing, to be honest, and it's hard to explain as well. But yeah, and by the way, a general note, a parameter is something that the model adjusts by itself, and a hyperparameter is something that we adjust.
Wait, can you say that again?
Never mind. I don't want to add a new thing to it. I'll explain it next time. Don't get worried. Don't worry about it. Shri said, so validation is where you change your parameters and then you train the training data with the new parameters and keep going until optimal accuracy. Yeah, okay, Shreyas, read that. That was a very good explanation. Yeah, you nailed it. You nailed it. Go ahead and read that in the Zoom chat, Shreyas. I think Shri couldn't have put it better.
Okay. I got it.
Hopefully that makes sense. And to anyone else that was having confusion, yeah. All right. I hope overfitting and underfitting makes sense. I think we got a lot of thumbs up on that, so we should be good. Please ask if it was confusing. Overfitting, underfitting, and then I hope this good model makes sense. Okay. I'm probably being confusing by graphing test set. This is validation set. Yeah. Unfortunately, I was correct when I wrote test set, but I don't want to confuse you, so I'm going to put validation set here. Maybe this makes more sense now. This is all during training. Validation set. So this should maybe show you what that really means. Like Shri said, validation is where you train your parameters and then you train your training data on the new parameters, right? So that's what we're doing. That's why these measurements are taken at the same time. They're both taken during our training, and we kind of measure the error on our training and our validation data sets, if that makes sense now. Hopefully you understand how this is an example of overfitting, where the validation set began to be bad, I guess. Yeah. Yeah, this was something, I hope you understood it, but I hope you found this comparison between biological neurons and artificial neurons or perceptrons pretty neat. I thought this was very, very neat when I first learned about neural networks. And I hope you understand that it can be boiled down to simply an input and an output, right? Just passing in some x, turning it into an f of x, and taking out some y. But it's not that simple. We still have our weights and we still have our biases, and that's what the perceptron is built on. And then we layer our perceptrons or our neurons to create an MLP, or a multi-layer perceptron, which is just a simple neural network, right? This is just a simple neural network. And once we have more than one hidden, or two or more hidden layers, right, which is just more than one hidden layers, that's where we have a deep neural network. And these are examples of neural networks that are densely connected, right? Every input is connected to every input neuron is connected to every single one of the output neurons to create a web of sorts. And last but not least, we have our regression models, and yeah, there's not that much to it. Any questions?
So, what was it you just talked about? Oh yeah, the weights and biases.
Yeah.
So you said they can vary between inputs, right?
Yes.
So do you determine them for each input, or does
No,
it
the model change. So they start off random. Weights and biases start off random from the computer, and then they get tuned by the validation data. That's the purpose of the validation data, is to test. It's like a checkpoint for the model. It's like a pop quiz almost. It's like a pop quiz for the model on unlabeled data, and then based on that pop quiz, the I guess that's actually a really good analogy. A pop quiz is a really good analogy, because when you take a pop quiz in class and let's say you do bad on it, right? And you know that you have a test the next day, right? So you're going to go home and study everything that you kind of failed on the pop quiz, right? So the pop quiz is the validation data, and the test set is, well, it's the test that you're taking the next day. And you're going to change what you know between the pop quiz and the test, right? You're going to adjust your brain's weights and biases, or the knowledge you have about that subject between the pop quiz and the test set. However, the validation data is a little bit more iterative like that. It's like having numerous pop quizzes. It's like having dozens of pop quizzes in order to test your knowledge to see whether or not you're up to speed. And hey, if you get 100 on the pop quiz, do you need to change your weights and biases? Probably not, because you did well on the pop quiz, so you probably have some sort of mastery of that concept, if that makes sense.
But exactly how are they determined?
That's what the black box of deep learning is. It learns it by itself.
So you don't. So you have to. So when you're running your validation data,
yeah,
you have to manually go in and adjust your weights and biases, or will your program identify that this is not doing good and it'll adjust the weights and biases?
It identifies it by itself. Yeah. Yeah, which is very, very weird to think about at first. Shri asks, can you overfit by changing the parameters too much and going too far? Yes, if you have a neural network that is too deep for a simple task, it will overfit. And that's what overfitting really means, is that you have a neural network that was really good on the training data, but it sucks on the validation data. So that's why you want to plot the validation and the training error to make sure that you're not overfitting. And I'm gonna purposely, like when we do some code, I'm gonna purposely overfit and then show you guys how to avoid that in the future. And we'll fix it together. But yeah, any other questions? These are some great questions. All right, looks like that was it. I hope you found this lesson interesting. I really enjoy teaching these stuff, even though it was just slides. Hopefully it was cool. And yeah, that's it for today's lesson. I will see you guys in the next one.
Thank you.
No problem. No problem, Shri.
Thank you.
No problem, Noah. No problem, everyone. I'll see you guys later.